All right, a quick, hopefully quick, lesson on probability. So this was covered in Integrated Algebra R. If you have old notes from Algebra 1, you might want to look at them because you did a lot of problems, I'm sure, back then. So first, the definition for probability. Probability is an estimate of the frequency of an event occurring still looks wrong, occurring in repeated trials. I think there's one C and two R's, sorry about that. No, two C's. I don't know why I can't spell occurring. Okay. The estimate of the frequency of an event occurring in repeated trials. And we have theoretical probability, which is based on theory. So, for example, the probability of tossing a coin and getting heads is 1 heads in 2 possibilities. So we say, theoretically, we know it's 1 out of 2. Empirical probability is when you actually run the experiment over and over and over. So for example, if we tossed a coin 100 times and we counted the number of heads and we only got 60, then that actual or empirical probability would be 60 for the event I was looking for out of 100, or 6 out of 10, or 3 out of 5, or 60%. So theoretically, we know it should be a 50-50 chance to get heads on a coin, but sometimes when we actually run an experiment, we get something different. Okay, let's go back up here. The probability of an event occurring, which is denoted with probability of, and then sometimes we write the event in here, is the number of elements in the event divided by the number of elements in the sample space. We drew out some sample spaces yesterday and figured out using the counting principle how many things were possible. So that ends up being part of today's lesson as well. Now we know that probability of any event will always come out between 0 and 1, and it could be 0 and it could be 1, so I'll use brackets there. If the probability of event is 0, it means there are no outcomes with that event. And we say an event like that is impossible. Like rolling a 7 on a die, that would be 0 because it's impossible. When the probability of an event equals 1, that's like 100%, then we say it is certain. And let's put 100% in parentheses there. If we know the probability of an event occurring, we can usually figure out the probability that the event will not occur. And something that's important here is that the probability of an event happening plus the probability of an event not happening is 1. These are referred to as complements of each other. Another way to look at that is if the probability of an event is P, then the probability of the event not happening is 1 minus P. And again, they are complements. We'll see one of those in our examples. Okay, so let's get rolling with some examples. What is the probability of rolling a die and getting a 5? Now, I won't do this every time, but we still could write out the sample space like we did yesterday. If we're rolling a die, we could get a 1, 2, 3, 4, 5, or 6. So there's our sample space. And we're looking at the probability now of getting a 5. So I look at my sample space and I see I have 1 5. 1 5 out of 6. So my probability is 1/6. How about not getting a 5? Well, how many of those are there? Not a 5, not a 5, not a 5, not a 5, not a 5. There are 5 of those out of 6. And here's a situation where we have complements of each other, because it's not getting a 5 and getting a 5. And you can see that those two add up to 1. All right, number 2. What is the probability of rolling a die and getting a number greater than 4? Well, my entire sample space of possibilities, there they are. I want a number greater than 4. So I've got 2 of those out of all 6. Number 3. What is the probability of flipping a coin? So the sample space for flipping a coin, I could get heads, I could get tails. I'm looking at getting a tail. There's 1 tail out of 2. So I'm breaking this down, trying to make it real simple. When we get tougher problems, writing out the sample space might help you, and examining the particular event might help you. Number 4. What is the probability of rolling a die and getting a number greater than 3 and odd? All right, rolling a die, sample space, we're using it a lot. There it is. Now I want a number greater than 3, so that could be any of these. But I've also added in that I need it to be odd. So 5 is the only element for my event. So my event has 1 item in it out of 6. Now number 5 is a little bit different. This one, instead of an and, has an or in the question. And so I'll tell you, anytime you see or, that's an indication that you're going to be adding some probabilities together. So it says I'm going to draw a card from a deck. There's 52 cards total in a deck. So there's 52 ways. I could draw them all out for my sample space, but I'm not going to. What is the probability of drawing a king? There's 4 of those. Or a black card. There are 26 black cards. So let's see. The probability of a king or a black card would equal the probability of a king plus the probability of a black card. But we have a little issue with this particular problem. Look at this picture right here. The king of clubs will be counted in this probability and in this probability. And the king of spades will be counted twice. So those 2 probabilities are counted twice. And that will throw off our answer. So we need to subtract away the probability of the black king cards, because it's going to be counted, they're going to be counted twice. All right, so I have to squeeze this all in now. Let's see what we got. The probability of getting a king is 4 out of 52, plus the probability of getting a black card is 26 out of 52. And now we're going to subtract off these 2 kings, the king of spades and the king of clubs, because they've been counted twice. And so the final answer here is 28 out of 52. Let me circle answers for these so we don't lose them. Now, one of the things I get asked a lot is, should we reduce or do we have to reduce with probability? You really don't have to reduce with probability, but you might see the answer in reduced form. as maybe a multiple choice question or whatever. So just be aware that you can reduce it, but typically you don't have to. Okay, number 6. An urn contains 12 marbles. 6 of them are red, 4 are blue, and 2 are yellow. What's the probability that we reach in and select a blue marble? So the probability of blue equals the number of blue over the total. Remember, if you go all the way back to the definition of probability, your numerator is the number in your event. So I know I have 4 blue, and your denominator is the total number in your sample space. And we have 12 marbles. Part B. What about not selecting a blue marble? Not selecting a blue marble. So not this one over here. Well, we know not selecting a blue marble should be 1 minus the probability of selecting blue, because they're complements. So that would be 1 minus 4/12 or 8/12. Another way to do it is to say, well, I know I have 12 marbles total. How many of them are not blue? 6 red, 2 yellow. There's 8 that are not blue. A couple ways to do that one. At any time you want to try these on your own, just hit pause and try a couple. It's good for you. A letter is selected at random from the word trapezoid. Find the probability that the letter is a vowel or a D. So we want probability of vowel, oops, or D. Now, or means you're going to be adding, and like the King of Spades, King of Clubs problem, watch out for overlap when you're adding. So let's see. I need the probability of a vowel, and I'm going to add the probability of getting a D, and there is no overlap here, so the overlap would be 0. So we can just add these together. Now, picking a vowel out of all these letters, how many letters total? 1, 2, 3, 4, 5, 6, 7, 8, 9. So we've got 9 letters. How many vowels? How many in the event vowel? So 4 vowels, 4 9ths for the vowel, and for choosing the letter D, we have 1 D out of 9, and so altogether that probability is 5 9ths. Now these are going to get a little trickier just because we're going to add in some formulas and geometry. 8 and 9 both have circles in them and squares and some shaded regions. So let's back away a bit, read it, and make sure we know what we have to do. A circle is inscribed in a square whose sides measure 8 inches. So this is 8 by 8. A dart is thrown and lands somewhere inside the square. So that's sort of like your dartboard there. What is the probability to the nearest tenth that the dart does not land inside the circle? So we have this square, and in this case we're looking for the probability that the dart does not land in the circle, which would be the same as the probability the dart lands in the shaded section. So if it doesn't land in the circle, it lands in the shaded section. So we're going to need to figure out some areas here. The area of the square. is our total area that we're dealing with. So that's side squared, which is 8 squared. So the area of the square is 64 square units. We need to subtract away, we need the shaded area, so we need to subtract away the area of the circle. Area of circle is pi r squared. So our circle has a radius of halfway through, so 4. So 4 squared is 16. The area of our circle is 16 pi. So that means the area, move these up, the area of the shaded region which we need for our numerator would be the square minus the circle. So for our probability, we need the probability of the shaded area out of the entire area, 64 minus 16 pi, that's the event on top, out of the total area, the whole square on the bottom. It says to answer to the nearest tenth. I'll leave that up to you to compute. I left mine in terms of pi. Let's see if I have it here. The next one's going to need area as well. See if you can get a jump on me there. Waiting. I can't find my calculator. Okay. Number 9. Two circles have the same center. The radii of the circles are 3 and 5. So this one's 3, and this one is 5. So I already know I'm going to need the area of the small circle, of SM there, small circle, area of the large circle, and most likely we're going to need then the area of the shaded, which we'll just subtract. So you can get these areas by yourself, all 3 of them. Area of a circle is pi r squared. So the area of the small circle is 9 pi. Area of the large circle, 5 squared is 25 pi. And so shading, I would take the large circle area minus the smaller, and that is 16 pi. All right. Find the probability, A, that the dart will land in the shaded area. Awesome. So probability of shaded, your value for shaded goes on top, and the total, big total, is the large circle, 25 pi. So those pi's cancel, and you have 16 over 25. Part B, find the probability it will land in the smaller circle. So the area of the smaller circle on top, and the total area on the bottom. And that is 9 over 25. Not too bad. A few more examples. Let's see, we've got 2 more pages, so I'll skip around a little bit. Number 10, find the probability of picking 2 kings from a deck of cards when the first card is replaced. All right. So I want a king for my first card, and remember multiply, and I want a king for my second card, and we are going to replace them. So there's 52 cards in a deck. So out of 52, how many of them are kings? We've got 4 of them. And then I put that card back. So for my second probability, I still have 52 cards and I still have 4 kings. So this turns out to be 4 times 4 and 52 times 52. I actually reduced mine to 1/13 times 1/13 and have 1 over 169. That's the probability you get 2 kings in a row putting the first one back. What if you don't put the first one back? All right, so I'm doing these like counting principle questions, if you noticed. I want a king for my first card, and I want a king for my second card, but I'm not putting the first one back. All right, so king for my first card, we know that. 4 kings out of 52 cards. But now there's a card missing from your deck, so there's only 51 cards left. And if you got a king, there's only 3 kings left. So multiply across the top, across the bottom, and you could leave it like that or reduce it. That's the probability that you would choose 2 kings in a row. Okay, so now some chemistry book questions and math book questions. Let's see, what do we have? 8 chemistry books and 3 math books on a shelf. If you select 2 books, one after the other, so 2 books, I'll just go like this, like I was doing before. Here's the first book, and you pick another book. What is the probability that both books will be chemistry? So our probability is we're looking for that we get chem books, chem and then chem again, chem and chem. So the probability the first book is chemistry, 8 of those, out of how many books? 11. Now that that chemistry book is chosen, I'm looking at the probability my second one is chemistry. But if my first one was chemistry, I'm down to 7 chem books, right? And I'm down to 10 total books. I'm going to read these very carefully. Number 13. There are 8 chemistry books and 3 math books. Same kind of question. If you select 2 books, one after the other, so book, book, book and book, what is the probability that the first one is a chemistry book? I read that backwards. What is the probability that you will select a chemistry book first? That's 8 chem books out of 11. So now there's a chem book gone. And a math book second. Well, there's 3 math books, but only 10 books. So that is 24 out of 110. All right. 14. There are 8 chemistry books, 3 math books. If you select 2 books, one after the other, what is the probability we'll select a chemistry book and a math book? All right, one after the other. So I'm going to choose a book and I'm going to choose a second book. Now, they're not telling us about the order. So they're not specifying the order. And when I write things out like this, I am ordering them. You know, up here it was chem and then math. So here, I have to do the chem and math, then I also have to assume that I could choose math first and then chem. So we have to do chem and math or math and chem. Just because of the way the question is ordered. So let's start this out. What what's the probability I pick chem first? Now chem book's gone. And math second. Okay, and then a math book's gone. But the other way this could happen was math book first, and then chem book second. All right, so chem math or math chem. And this will turn out to be 48 out of 110. Whew. Okay, getting a little sick of chemistry and math books here. Why don't you try this one on your own? Block it off, decide what you want. Okay, it says, what is the probability that both books will be the same? So what could we get if both books are the same? We could get chem, or we could get math. Aha. So you go ahead and figure out chem, or math. And on the back, we'll just do a couple more. 16, the following 6 students are asked to line up. Brian, Mike, Emily, Krista, Ronald, and Andrew. So if they're asked to line up, order matters. So I've got 1, 2, 3, 4, 5, 6. Yep, 6 students. Okay, we can do this if they're going to line up. What is the probability that if they line up, a girl is first? So I'm going to put the probability of getting a girl first and a boy is last. All right, girl first, boy last. So what is the probability of placing a girl first? We've got Emily and Krista, 2 girls out of 6. And then we're going to go to the boy last because they're not telling us anything about these other 4 spots. So the probability now of choosing one of the boys, there is 1 less student in the total. Let's just say Emily was chosen. So there's 5 students and 4 of them are boys. So the probability that a boy would be placed last is 4 out of 5. Now, they are not concerned with the other 4 spots. I have 4 kids left and 4 options. Then I have 3 kids left and 3 options. 2 kids left and 2 options, and 1 kid out of 1 option. Notice these are all equal to 1. And the problem only cared about the girl first and the boy last. So that's 8 out of 30. I think that's good. I can do these last 3 in class with you. We'll obviously be practicing in our books as well. See you tomorrow.